Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This subject is the first paper in the first semester of the course. This lecture is the 43rd lecture in the series. Of late, we are discussing about the functioning of a transistor. In continuation to that, in today's lecture, we are going to see the different modes in which a transistor could be used. Before we start the lecture, let us see the outline of today's lecture. In this session, we are going to see the transistor characteristics in common base mode and common collector mode, and also we are going to compare the modes with the common emitter mode. In the earlier lectures, we have seen a transistor could be used in three different modes. Because it has three terminals and it is a bipolar device, we need two poles or two terminals for the input and two terminals for the output. But we have only three terminals available in a transistor. How to make use of these three terminals for a four-terminal device? Two terminals for input and two terminals for output. We have to keep one terminal common for both input and output. Because of this condition, we can have three different types of connections. Either we can keep the base as a common for both input and output, or emitter as common, or collector as common. We have just touched upon these three types of modes in one of the earlier lectures, and then we have discussed the common emitter mode, that too for the NPN transistor elaborately. We have studied the characteristics of the transistor in the common emitter mode and what are the information we get from the input characteristics of the common emitter configuration and output characteristics of the common emitter configuration. The parameters that we could get from the characteristics we have discussed elaborately in the earlier lectures, and also based on the characteristics, the suitability of using the transistor either as a switch or as an amplifier. All these concepts we have dealt at length in the earlier lectures. But still, one topic is pending. That topic is what we are going to see today. It is comparison of the common emitter mode with the other two modes, or vice versa, the common collector and common base mode. We have to compare all these three modes and find out in which mode the transistor could be used for a particular application. Why it was delayed, why it was not taken up for discussion in the earlier lectures? The reason was we need to get some idea about the parameters that we need to consider when we want to analyze the different modes of operation. We have taken up one, for example, the common emitter configuration, the input, output, transfer, all the characteristics have been analyzed, and we have got an idea now what are the parameters that could be measured from the characteristic curves. The one is the input impedance, the other one is the voltage gain, and one more is the current gain, and another one is the output impedance. These are the four common parameters normally we study as far as the characteristic study of any mode is concerned. Now we know what is the input impedance, what is the meaning of the current gain, voltage gain, output impedance, etc. With this knowledge that you have got for the common emitter configuration, now we are going to take up the other modes of operation or other configurations of the transistor, namely the common base mode and the common emitter mode. We have got some idea about the current amplification that's possible in common base mode, because in one of the earlier lectures we have found the relation between the terms alpha and beta. Alpha is the current gain in the common base mode and beta is the current gain in the common emitter mode. We have established a relation for these alpha and beta terms. So with this background now, it's ideal time for us to go for the other modes of operation and then compare the parameters, compare the modes with the common emitter mode for the suitable operation of the transistor in a particular mode. So let us now start our discussion with the common base mode. Before we start the discussion, we need to know what is the biasing condition. We are familiar with the biasing condition for common emitter mode. Now let us brush up the general rule for biasing of a transistor so that we can take it forward for the study of the common base mode and common emitter mode. So let us have a look at the general rule for biasing. It's a very simple rule. The input side is to be forward biased and the output side is to be reverse biased. Actually, based on the region, the emitter and base region, and then base and collector region, which is to be forward biased, which is to be reverse biased, all these we have learnt at length in the earlier lectures. But I have given a consolidated rule, very simple rule to follow for whatever mode of operation. As far as a transistor is concerned, we have an input side and an output side. Having this in mind, we can easily keep the rule in mind. Input side is to be forward biased and output side is to be reverse biased. Whatever be the configuration, whatever be the type of transistor, this general rule will always be very helpful. So let us have a look at the rule and then go ahead with the application of this rule for the common base configuration. Input side is forward biased and output side is reverse biased. Now let us take the case of common base configuration. This is a schematic representation of the characteristics of transistor in the common base mode. Because we are now familiar with the connections, the biasing conditions with the general rule in mind, I have avoided the power supplies which give the biasing for the input and output side. Because we are very familiar with the connections now, I have just taken the transistor alone and shown the quantities that are to be measured, like the current and voltage on the input side and current and voltage on the output side. The polarity and the power supplies related to the biasing are not given in the diagram. It's a very simple lucid diagram which could be taken up for discussion. This is a common base mode configuration. The input side current is here, the emitter current, and the output side current is the collector current, and here the base is kept common for the input and output side. Similarly, the input side voltage is VBE and the output side voltage is VCB. Now, we can take up the input characteristic study of this simple circuit. How the input characteristic curves look like? Let's have a look at the diagram. This is the input characteristics of the transistor in the common base mode. We have taken, as usual, the voltage on the x-axis and current on the y-axis. The voltage here is VEB and the current here is IE, the emitter current in milliampere, is taken on the y-axis. Now, by maintaining the VCB constant, maybe at several values, first we have to maintain it at one value and take the dependence or vary any one quantity like the VEB, and what is the change in the IE. We need to note and plot a graph. This graph is drawn for three different values of the output voltage. The output voltage is VCB. Once we have a look at the diagram, we are reminded of the forward biasing of the diode. It is somehow similar to the forward biasing of the transistor in the common emitter mode. There is no much change in the trend of the graph. It is somewhat similar to the common emitter configuration forward input characteristic curve. And by taking the slopes, the inverse of the slopes especially, we can find the input impedance and the voltage gain, etc. It is the same calculation what we have carried out for the common emitter mode is to be done here for the common base mode also. Now, let's have a look at the output characteristics. The output characteristics has some additional features. This is the output characteristics curve of the transistor in the common base mode. Here also we have the three regions like saturation region, cutoff region and active region, etc. But along with that we have shown one breakdown region. This is what I wanted to highlight today. And another important change is the saturation region is not found on this side. In the case of common emitter mode, all the graphs, all the curves started from the positive side of 0, it went like that, but here it is starting from the other side of the y-axis. So, this is because of the biasing, this is because of the values of the VCB required for forward and reverse biasing the transistor. And the breakdown region occurs when the VCB value is very high. This kind of breakdown is possible even in all the modes like common emitter mode, common base mode and common collector mode. This breakdown region would be possible when the reverse bias is too high for the transistor to withstand. Even in the case of a diode, when the reverse bias voltage is too high, the diode would physically get damaged. That we learned in the earlier lectures. The same thing is applicable even for a transistor. Of course, a transistor is made up of two PN junctions or three regions. So, two PN junctions are there. So, these junctions are subject to the breakdown phenomenon when the reverse bias voltage is too high. So, here also in the case of common base, when the VCB is very high, because it is in the reverse biased condition, the breakdown would occur. But otherwise, when it is in the safe limit, the trend is very useful. Let's have a look at the trend. Here, the knee voltage is occurring exactly at the 0 value of VCB itself. Let's have the circuit diagram. Let's see where the VCB is applied. And this is the VCB. This VCB, even if it is not having any potential, even if it is having a zero value, the collector current seem to reach a maximum value. That is what is represented in this output characteristics curve. And if we reduce the voltage VCB to the other side of the polarity, then there itself the saturation region exists. Now, 4 points are to be kept in mind as far as the common base mode is concerned. Even when the IE is 0, a small current flows. This is I, it's represented as ICBO in the curve, the reverse current through the reverse biased collector base junction. The second point is for VCB greater than 0, the characteristics are essentially flat, that is IC is independent of VCB. Hence, the output resistance is large. In reality, there is a finite slope on the flat sections because alpha varies with IC and VCB. Here, alpha is the current gain. We can note also that in these flat regions, IC is approximately equal to IE since alpha is approximately equal to 1. In practice, the alpha is slightly less than 1. It can never be greater than 1. The third point is at large values of VCB, the characteristics turns up due to the breakdown at the reverse bias collector base junction. The fourth point is the characteristics fall rapidly to 0 for VCB less than 0, that is when the collector base junction becomes forward biased. Normally, the collector base junction is to be reverse biased, that we should keep in mind. Even when we forward bias it, there is a rapid decrease in the current, the output current, IC current. So, these are the main features of the output characteristics of the transistor in the common base mode. Now, it is time for us to take up the next mode. It is common emitter mode. Let us have a look at the circuit for the common collector mode. In the common collector mode, we have the connections like this. The collector is made common for both the input and output. Here, the potential between the emitter and base terminals should be greater than 0.7 to make the transistor come to the on state. So, that is why it is marked here, and the output is taken from the emitter itself. So, it is given a name emitter follower. What is an emitter follower? Because in common collector mode configuration, the output is taken from the emitter, so it is called the emitter follower circuit. In most of the textbooks, the common collector mode name would not be used, but it is simply represented as the emitter follower. Whenever this terminology comes, we should keep in mind that it is a common collector mode. In common collector mode, how the characteristics look like? Let us take the case of the input characteristics. This is the input characteristics of the transistor in common collector mode. As I have shown in the diagram, the VBE, if it is approximately 0.7 and above, the transistor is on. The VEB, when we write the Kirchhoff's voltage law for the junction, this is the equation we will get. So, that is why the value, I'll come to this region after explaining the off condition. If the VBE is less than 0.7 or approaching 0, the VCB will be almost equal to VCE itself. So, it is represented here in the graph very well with these values of 0.7, and for one example, let us take it is the 5 volt is the VCE maintained constant. What happens when the input current is less, very less, it is not able to bring this 0.7 volt across the base emitter junction. So, that is why this law, this formula is applicable. The VCB is VECE minus 0.7. So, it is 0.7 less, and after that when the 0.7 is not reached, when the base current is less, VBE will also be less. So, in that condition it will be almost equal to the VEB. The VCB will be equal to VCE itself. So that is represented here. It appears as if the transistor has a negative resistance. So about this we will have to discuss at a later stage. But right now, based on this condition, this graph or this trend is obtained. That's what we have to keep in mind. Now what about the output characteristics? Let's quickly have a look at the trend of output characteristics. After that we will be able to compare the three modes of operation of transistor. This is the output characteristics curve, and here also we have the breakdown region. Normally this breakdown region is not much highlighted in the characteristics curves because we will not take the transistor to that extent. And here we have the cutoff region below the IB, less than the IB is 0 and below it is the cutoff region. The saturation region is found very well in the positive side of the VCE itself. We should keep in mind the VCE is a reverse biased voltage, that we have to keep in mind. And the active region has got a slope and it is almost tending to saturate. It has got a slope here, and it's otherwise similar to the regular trend we have for the output characteristic curve. And now, having all these concepts in mind, now it's time for us to have a comparison for the CE, CB and CC modes of operation. Let's have a look at the comparison table. It's very nicely represented. Here in this column they have taken all the characteristic features like input impedance, output impedance, the phase angle between the input and output waves. Actually this phase angle we will elaborately discuss when we consider the transistor as an amplifier. We are yet to develop the concepts of transistor as an amplifier. In the upcoming lectures we will be able to take it up, but right now it gives us some idea. And again the voltage gain and the current gain and the power gain. What is power gain? Power gain is the product of voltage and current gain. So far we have not touched upon the current gain. We have restricted our discussion with only the voltage gain and the current gain, but power gain is nothing but the product of these two. When we learn about the power amplification of the devices, we will give importance to the power gain, but nevertheless it's compared here just for the sake of comparison. Now let's have the trend of the values for these three modes of operation. Let's have a look at the table again. In the common base mode, the input impedance is low and the output impedance is high. The phase difference between the input and output waves is 0, voltage gain is high and the current gain is low, power gain is low. Similarly, for the common emitter mode, input impedance is a medium value, output impedance is a high value, there is a phase reversal of 180, we call that as out of phase, and voltage gain is moderately high, or it's mentioned here as medium, and current gain is medium, and the power gain is very high. When we multiply the two medium values, we get a very high value. And for the common collector, input impedance is high, output impedance is low, no phase reversal, voltage gain is low, current gain is high and the power gain is medium. This gives us the nutshell of the three modes of operation. It's very well mentioned in the curriculum of the course, the comparison as a topic. So that's why we are comparing the three modes of operation. The few points I would like to highlight: when we take the power gain, it's very high in the case of common emitter. That's why the common emitter mode is the most preferred mode of operation. This also I have already mentioned. And when we look at the input impedance between the common emitter and the common collector, it is just the opposite. The input impedance is low here and medium here, it's very high. It is the opposite trend. And output impedance is high and very high and high here for the common base and emitter mode, but in the common collector mode, it is the lowest value. So, as far as the impedance is concerned, these two are somewhat similar. Common base and common emitter modes of operation are similar, and this is something different. It's just the reverse of these two modes of operation. And the other points are also important here. We can use them whenever we take it up for discussion. Now, based on the impedance values, the common emitter, the common base mode and common collector mode have their own applications. The common emitter we are discussing, we have taken up for discussion elaborately in the previous lectures, and also in the future lectures we will be discussing mainly about the common emitter. But now let's see the common base and common emitter application. Let's have the application of common base and common emitter configurations. The common base has got a good use in the frequency response range. Let's have what it is. The CB mode is generally only used in single stage amplifier circuits such as microphone, preamplifier or RF radio amplifiers due to its very good high frequency response. So, whenever we want to use common base, it is used for this property, the frequency response. It responds properly and nicely for the RF range. So, that is why it is used as a microphone amplifier or preamplifier in the RF radio range, frequency range. For that purpose it is used. And what is the use of the transistor in the common collector mode? Mainly it is because of the impedance feature, low input impedance and high output impedance. Because of that, how it is used? Let's see what is the application. The emitter follower configuration or common collector configuration is very useful for impedance matching applications because of very high input impedance in hundreds of thousands of ohms, and it has relatively low output impedance. It is also termed as buffer for this reason, and it is used in digital circuits with basic gates. The common collector configuration is mainly used as a buffer. It will not amplify, but only for impedance matching it is used. So, these are the applications of the transistor in the common emitter and common base mode. Now, it is time for us to see the summary of today's lecture. Let us see the summary. In this session, we have seen the transistor characteristics in common base mode and common collector mode and compared the features with the common emitter mode. Let us test our understanding by answering these questions. Discuss the transistor characteristics in CB mode. Brief the transistor characteristics in CC mode. Compare the characteristics of transistor in common base, common emitter and common collector modes and mention their applications. So, we have compared the transistor in 3 modes of operations in this lecture. We will see the other aspects of transistor, especially the application as amplifier in the subsequent lectures. I would like to wind up this lecture with these concepts. See you in the next lecture.